So I want to show that f is satisfiable implies G has a Hamiltonian cycle, right? Directed Hamiltonian cycle. Okay. Without the CIs, we know that this graph has Hamiltonian cycle. In fact, lots of Hamiltonian cycles. So it's just the CIs which we want to make sure that they will be able to, you will be able to take them and visit them, right? So now, one direction of the proof, if f is satisfiable, what does that mean? There exists some assignment for x1, x2, xn such that every clause is satisfied, right? Good. So now here is my Hamiltonian cycle. I will start from S, and then what do I do? So there is some assignment, right? That assignment tells me x1 is 1, x2 is 1, x3 is 0, x5 is 0, and so on. Somebody has given me that assignment. Now, based on the assignment, I am going to give you a directed Hamiltonian cycle. So what should I do? So let's say x1 is 1, then what do I do? So my Hamiltonian cycle will start from S and say, oh, x1 is 1, so I am going to traverse this path from left to right. So I will traverse it this way. And then I'll ask you what is x2? x2 is 0, then I'll come down and traverse x2 in this direction. x3 is 0, I'll come down again and traverse in this direction, and so on and so forth. But I have only traversed these paths, I have not traversed the CIs yet. Okay. So now how do I traverse the CI? I'll ask you, okay, C1, who is satisfying you, right? They told me that it is a satisfying assignment. Who is satisfying you? You might say, oh, x7 is 0 is satisfying C1. Okay. So since x7 is 0, we traversed x7 in this direction. And in this direction, we have actually, remember in the first block, we have added the edge so that C1 can be included there. So now I break that path, go and take C1 and come back and continue. And I ask this for every clause. There will be something which is satisfying, which is based on the assignment, and in that path I have constructed in a way that I can go and include that corresponding clause. So at the end of it, so I'll finish that, come back to T and go back to S, and I have a Hamiltonian cycle which visits every clause as well, right? This is one direction, right? I am not written down the proof. This is one direction. The converse, so okay, so let me just write a one line proof of it. So traverse the paths based on the satisfying assignment. Okay, so it's high level, and include the CIs based on the variable that satisfies that clause. And converse is pretty much the same. If this graph has a Hamiltonian cycle, remove the CIs from the Hamiltonian cycle, look at how these paths are traversed, that will give you an assignment, right? If this path is traversed this way, x1 is set to 1, otherwise x1 is set to 0. Okay, that gives you an assignment. So from the Hamiltonian cycle, remove the CIs, look at how these paths are traversed, that gives you an assignment, because we said every Hamiltonian cycle corresponds to an assignment and vice versa. And now I have to argue that that assignment actually satisfies every clause. Well, how do we argue this? Well, your Hamiltonian cycle includes every clause. So go and see who took care of CI, the clause CI. In the Hamiltonian cycle, it just came here and went back and picked it up. And so that tells you that that assignment would actually satisfy it. Okay. And there are a few more details, like you have to have a Hamiltonian cycle in this particular way, because you can't come back, pick some CI and go back to some other path. All that is possible, but then if you do that, you will be stuck, because there will be some degree 2 vertices that you cannot visit. Okay. So those are some case analysis you have to do. So there are some 2-3 pages of proof actually, but the high level idea is this. Okay. I think this is relatively simpler reduction than the vertex cover to Hamiltonian cycle we saw yesterday. Okay, so I'm not giving you the complete proofs, but we sort of carefully constructed the graph with the goal in mind that everything will fall in place once you've done this. Okay, so now I want to show that, let's go back to undirected graphs. I want to show that Hamiltonian path problem is also NP hard, right? So what is a Hamiltonian path problem? Given a graph, is there a path that visits every vertex exactly once? Okay, Hamiltonian cycle asks for a cycle, but here I am looking for a Hamiltonian path, a path that visits every vertex exactly once, and you expect that this will also be hard, right? Because Hamiltonian cycle is hard, but you don't expect it to be easier. But let's try and prove it, right? Now the proof is not hard, but let's do carefully go through the process, right? So we want to show that okay, so what is the problem? Given graph G, is there a path, a simple path Okay, so how do we start? See, this is exactly what I expected. Right? What do you have to do to show it is NP complete? Start from the basics, right? What do you mean by forward direction? We haven't even set up anything, right? But I'm glad you said it because I'm sure everybody makes this mistake. That's why I want to go through it slowly. So we want to reduce from a known hard problem to this problem. So what is the known hard problem we want to pick up? A natural choice is Hamiltonian cycle, right? Good. So we are going to reduce Hamiltonian cycle to Hamiltonian path problem. Okay. Let me actually interpret what you just said. I think I know what you're saying. You're saying that in any graph, if there is a Hamiltonian cycle, there is a Hamiltonian path. That's what you meant, right? This is clear. If there is a Hamiltonian cycle, there must be a Hamiltonian path. But the converse need not be true. Hamiltonian path exists, may or may not mean Hamiltonian cycle exists, right? So in particular, just directly on the same graph, I can't give it to my Hamiltonian path problem and find whether a Hamiltonian cycle exists or not. Suppose one reduction, maybe I know you're jumping ahead. This is what you probably meant, that what is the problem here? Given a graph, is there a Hamiltonian cycle? And your reduction is, maybe give the same graph, right? Suppose I do this reduction, then what do I need to show? If G has a Hamiltonian cycle, G has a Hamiltonian path, and if G has a Hamiltonian path, G has a Hamiltonian. So converse is not true, need not be true. So you need to do a little bit more work. Okay, just given the same graph is not enough. Okay, somehow you have to transform it, do something to your graph so that existence of the Hamiltonian path here would actually give you a Hamiltonian cycle here. What does that tell you about our original graph? Okay, so what you are saying is I take my graph, I make it complete. Go back to my template, okay, always keep that in mind. I want to show that if G has a Hamiltonian cycle, this G prime has a Hamiltonian path, and if G prime has a Hamiltonian path, G has a Hamiltonian cycle, right? But you just told me that this G prime will always have a Hamiltonian path. because you made it complete, right? So if I have, this is my graph, and you will translate it like this because you want to make it complete. And existence of Hamiltonian path is always guaranteed. Remember, this is what I started out with, that construction when I did my 3-sat to Hamiltonian cycle, and said this always has a Hamiltonian cycle, but I threw in clause variables and added some edges that twisted the construction, so that sometimes it may not exist, right? Okay, so keep the goal in mind, and you need to do more work. Okay, so let's stick to undirected graph. Okay, it's all more or less the same, but one trick is, suppose I add some pendant vertex. So the point is, there are lots of Hamiltonian paths. So you want to be able to pull out a Hamiltonian cycle from a Hamiltonian path, right? So you have to do more things. You have to add something to the graph, and then okay. So what I am going to do is the following. Assuming I know correctly what to do. So I will take my graph. So graph looks like this. I'm going to pick some vertex V in the graph, okay, and make 2 copies of it. See, I'm talking in general, complete ways, right? That's something I want you to keep in mind, right? I picked some arbitrary vertex V and I made 2 copies of that, and I'm going to add an edge like this. Okay, these 2 vertices, let's call it V1 prime and V2 prime. They are going to be pendant vertices. No more edges will be added, right? If I add no more edges, then if the graph has a Hamiltonian, I haven't told you what the rest of the graph is, I will tell you, but before that, if the graph has a Hamiltonian path here, what can you say?
It starts from V1 prime and ends.
Very good. It must start at the 2 endpoints must be V1 prime and V2 prime. That's the control I want to have, right? Okay. Now because my goal is, from a Hamiltonian path, I want to be able to pull a Hamiltonian cycle. So I want to have some control on the Hamiltonian path so that I can recover my Hamiltonian cycle. To get that control, I'm adding these pendant vertices, because then I know that these pendant vertices will be start and end points of my Hamiltonian path. Okay. Now, how does the rest of the graph look like? So this is my G minus V, right? Because I've deleted V from here and I made 2 copies. And V1 and V2 will be adjacent to whatever V was adjacent to. Now that's my G prime. Okay, is my G prime clear? G prime, I take G, I delete one vertex, make 2 copies of that, add this pendant vertex, and whatever V was adjacent to, this V1 and V2 will be adjacent to that. Okay. Now my claim is, what do I have to show? If G has a Hamiltonian cycle, G prime will have Hamiltonian path, and if G prime has a Hamiltonian path, G will have a Hamiltonian cycle. He has already seen the proof now, right? He is nodding. He sees the proof. Good. Let's see the proof, right? The claim, G has a Hamiltonian cycle if and only if G prime has a Hamiltonian path. Okay, let's prove the forward direction. G has a Hamiltonian cycle, right? This cycle in G will go and visit every vertex, and V is one such vertex, right? In graph. So now from this Hamiltonian cycle, I am going to get a Hamiltonian path for G prime. How does that path look like? Starting from V1 prime, it will go to V1, and starting from V2 prime, it will go to V2, right? This we already established. What else do I do? What? Yeah. So this Hamiltonian cycle, V has two neighbors, right? X and Y in this Hamiltonian cycle. Remember, I am getting my Hamiltonian path from this Hamiltonian cycle. So V1 will go to X, but V1 may not be adjacent to X. V1 is adjacent to X. Why? V1 must be adjacent to X. Why? Because I made the construction ensure that V's neighbors, whatever V was adjacent to, V1 and V2 was adjacent to. So if this Hamiltonian cycle, X and Y were adjacent to V in the graph, so V1 also X will be adjacent, Y will be adjacent to both V1 and V2. I have no problem. So from X, I will traverse the rest of this cycle, come up to Y, then go to V2. That's my Hamiltonian path. It's a path. It visits every vertex exactly once because this was a Hamiltonian cycle. It visited everything exactly once. So I've got a Hamiltonian path here. Right? If G has a Hamiltonian cycle, G prime has a Hamiltonian path. I just spliced my vertex V and made two copies of it. So I can take my Hamiltonian cycle and convert it into a Hamiltonian path. The converse is pretty much exactly similar, because if G prime has a Hamiltonian path, we know that it must start at V1 prime because V1 prime is a degree 1 vertex and it has no other place to go except to V1, and it should, at least this portion of the Hamiltonian path must be like this. After that, whatever the Hamiltonian path is visiting, splice this because V1 and V2 have the same neighbors as the same as V. So that would give me a Hamiltonian cycle here. Right? So in all the problems in your problem sheet, you need to do something very simple, something similar like this. Okay, we didn't do very complicated thing, not like a big gadget I did from 3-sat to Hamiltonian cycle or vertex cover, but you realize that these two are related, but somehow in the same graph, Hamiltonian path may not mean Hamiltonian cycle, so I need to do a little bit more work to get this. Good. Okay. So, in fact, most of the problems are even easier than this. Okay. Let's do the chromatic number, the graph coloring problem, right? Yesterday afternoon we were talking about minimum number of colors you need to color a graph. There are some greedy algorithms. Order the vertices, pick a vertex, give it color, and just run through your ordering and pick a vertex. Give a color which is the smallest available color. Okay, that is one greedy algorithm, and there is an exercise in your problem sheet which tells you that this greedy algorithm not only does not give you optimum, it can be extremely far from the optimum. Okay, optimum may be 2, but your greedy algorithm may give you 2000. Right? It can be as bad as far away from optimum. Okay. Now, what I want to know, what is the minimum number of colors you need to color the vertices such that adjacent vertices get different colors. Right? When can you color the whole graph with one color? When there are no edges in the graph, you can color with one color. When can you color it with two colors? If the graph is bipartite. You can actually check that in linear time, right? Doing BFS and all that. Now, next question. So I don't even want to know what is the minimum number of colors, but suppose I want to know, is it even colorable with 3 colors, right? And we saw examples that, for example, if you have a triangle in the graph, you need at least 3 colors. But she was also giving you an example where a triangle free graph, but still it may need a lot of colors. In fact, arbitrarily any number you choose, there is a graph which does not have a triangle, but still the minimum number of colors is large. Okay, so existence of a triangle is just one condition. It's not, it's a sufficient condition to say that you need 3 colors, but that's not necessary. Okay, and what we will show is actually testing whether a graph is 3 colorable is NP complete. Okay, so there is no easy algorithm, and no wonder that any of these greedy algorithms do not give you optimum solution. Okay, so what is the 3 coloring problem? Given G, so coloring is just a function from the vertex set to numbers 1, 2, 3, such that whenever ij is an edge, color of I is different from color of j. And what we will do is we will reduce. So again, I am not proving that the problem is in NP. How do you show it is in NP? Yeah. So what is the certificate proof? A 3 coloring. So you give a 3 coloring, and that's a proof. You run through every edge in order m plus n time, check that both endpoints get different colors.
One of the arguments say that there is no possible free coloring, and how do you verify that there is no possible free coloring?
Aha. Yes, somebody wants to answer. So he says, okay, if you give me a 3 coloring, I can verify. But if you tell me that it is not a 3 coloring, how do you verify? Good question. If you go back to my definition of NP, what is the definition of NP? The yes answer has a certificate which can be verified in polynomial term. I made no claims about no answer. Okay. In fact, there is a class of problems called co-NP. Good, you brought it up, where the no answer can be verified in polynomial term. Okay, that's also a class of problems where decision problems where the no answer has a certificate which can be verified in polynomial time. We will get to that and see some examples. Okay, my reduction. So how do I show it's NP hard? I have to pick a known NP hard problem, reduce it in polynomial time to my graph coloring problem. And the problem I'm going to choose is again 3 sat. So input here is some variables and some clauses. And the input here is, what is the input here? A graph. I have to just get a graph, right? So this graph is going to have a lot of triangles. So you need at least 3 colors, but 3 colors may not be enough. And we will construct the graph in a way that it is 3 colorable only if this formula will be satisfiable.